Hello, my name is Jake Maier, and my term project for CS528 is named DiceVision, a dice detection project. I chose this project because I am a frequent player of the tabletop role-playing game Dungeons & Dragons. We play roughly once a week. Recently, two of my players moved out of town and have been joining us to play remotely online and have substituted their physical dice rolls with an online number generator. DiceVision is an attempt to reintroduce the fun and tactile experience for these players with rolling a physical dice by detecting the dice rolls with computer vision. The model is trained to identify the 6 standard dice shapes used in most TTRPGs: D4, D6, D8, D10, D12, and D20. Along with a model, I created a simple GUI that displays a live preview of the camera, along with a single button that, when clicked, runs inference on a snapshot and uploads the detected dice results to a Discord channel that the TTRPG group utilizes. Sure, the player could just tell us what they rolled, but DiceVision offers validation on top of that by attaching the image of the annotated dice roll to the upload as well. The program is developed to run on a Raspberry Pi 5. I attached mine with an AI hat and the Raspberry Pi Camera Module 3. I found that public datasets of dice images were not sufficient for this use. Most that I found were simple cube D6 dice, commonly used in board games like Yahtzee, Catan, or Monopoly, and that is not what I need for TTRPG use. Because of that, I had to make my own dataset. From what I heard about large language models and the relatively small datasets we use in our class, I was under the assumption that I would need a massive dataset to get good performance. I planned long group sessions with pizza and friends to capture thousands of dice rolls, but by the progress report, I only had 100 images and was surprised to be getting incredible performance. So I actually ended up only with 300 images in my final dataset, and I found that to be more than sufficient. However, this was likely only possible because I eliminated many real-world variables. All images were taken with the same lighting and the same background. Tailoring it in this way will increase accuracy, however, I expect it to be much less generalizable. I quickly decided not to do face detection, as I had seen related work describing that task as much more difficult, and the camera and lighting equipment I had at my disposal is not very impressive. There actually were a few projects I found online that looked to be doing similar things, although most were aimed at numerical face detection rather than polyhedral shape detection. They detailed the needs to have complicated lighting that eliminated shadows, using high contrast dice only, using massive amounts of data. Most people's desk setups when playing TTRPGs are not perfect conditions like that, so I personally find those requirements not to be fair. Thus, I required for DiceVision a simple overhead light and whatever dice you wanted to use. Most of the other works were not intended for edge device deployment either, so their models are also more computationally expensive. DiceVision differs by using a single stage detector with the YOLO V11 backbone. For this project, I captured 303 images with a total of 849 rolls in them. Each class of dice is roughly evenly represented with around 142 occurrences in the training data. I manually drew the rectangular bounding boxes and classified each over a few hours using RoboFlow Universe Online. For the model, I already mentioned that I ended up using YOLO V11, but I considered the older models RetinaNet and EfficientDet, but I found them harder to apply transfer learning to. YOLO V11 by Ultralytics has a very user-friendly API that made tailoring it quite simple. I trained the model for 100 epochs using Google Colab NVIDIA A100 GPU, and it took roughly 5 minutes. I exported the model to TensorFlow Lite for deployment without adding optional quantization, pruning, or clustering. I wrote a simple GUI application that runs DiceVision with a live camera preview and a single button to take a snapshot, run inference, and upload the results to Discord as shown here. Even with a dataset of under 100 images, the preliminary results were very surprising. On the validation set, I was seeing an overall precision of 0.927 and a recall of 0.882. However, that was on the validation set, so it's a little biased. When I ran it on some unseen test images, I was seeing low confidence results, misclassifications, and even missed dice. This is shown in the top image here. The final model, on the other hand, was trained with 300 images, and the result on the held out data set of 40 images was very good. The overall precision was 993, recall was 995, and the MAP 50 to 95 was 0.873. As shown in the bottom image, the predictions were more confident, we did not miss any dice, but we did still misclassify one D8 as a D20. In conclusion, DiceVision does a great job proving the feasibility of a model like this. Given a larger and more varied data set, I am sure that DiceVision could be more generalizable for people to download and utilize for their online TTRPG games. I was very surprised by the performance of transfer learning from Violo V11. The model must truly be an excellent baseline for even domain-specific fields such as this. I like DiceVision as it is, but I will not recommend it for my friends to use, because simply detecting polyhedral shapes is not yet that useful. We would need face detection, but until we can figure out how to handle glare and shadows in different dice trays with a variety of camera qualities, I would not recommend its use in my games. Thank you for listening in. This was a fun project and a great semester.